Well, thanks everyone for coming. In particular, I think my youngest ever audience member so far, behind the door. So yeah, I am here to talk about some work of mine with Andy Burgett on Speyer's conjecture, which sprang from his investigations of tropical linear spaces. Tropical linear spaces maybe being one of the core examples in my mind of this theme of geometry without geometry. Probably in this room, tropical geometry is a familiar beast. One can tropicalize algebraic geometry, algebraic varieties, and then sometimes one finds things which should count as tropical varieties, which aren't tropicalizations. So these are geometries in the tropical sense without geometries in the field sense. So tropical linear spaces were one of the first cases of this looked at by Speyer in his thesis. So I'll start by telling you how he defined those. So I want to get at them via matroid polytope subdivision. So I should start with matroid polytopes. If I'm writing too small or speaking too quiet or, I don't know, committing some other problem, just yell at me. I have a polytope. I call it a matroid polytope. Matroid basis polytope, some would say. Belonging to some matroid M. If its vertices are 0, 1 vectors and its edges are all in type A root directions. So this is not, this can be used as a definition of matroid. It is perhaps not a definition of matroid that one sees in any of the standard textbooks. Maybe that'll change one day. Let's not talk about that. I'm long overdue in a chapter for a textbook. This is cryptomorphic, if you like that word, to other matroid axiom systems. For instance, the basis axiom, this is called the basis polytope because I'm supposed to regard these vertices as encodings of the bases. So this polytope is the convex hull of the bases. So I won't give a lot of cryptomorphism, but I'll say the bases of M are the sets. Well, are the vertices read as indicator vectors of sets. So, for example, we can take the uniform matroid of rank 2 on 4 elements. So this is the matroid whose bases are going to be all size 2 subsets of a 4-element set. That gives us 6 vectors, of which we want to take the convex hull, all permutations of 1, 1, 0, 0. And if we do that, we get a polytope. Well, we get the octahedron, which I can draw. It lives in R4, but it lives in the hyperplane in R4, where all of the coordinates have, or the vertices have coordinate sum 2. So it looks like this. A picture I draw in a lot of talks. And you can see that there are 12 edges to this octahedron, but all of the edges are obtained by taking one vertex corresponding to one set, like the set 1, 2, and I move to another set, 1, 3. All I've done is subtracted 1 from the second coordinate, added 1 to the third coordinate. That's the legal direction for an edge. Right? The kind of things I don't have an edge, for instance, going down the middle like this. This isn't an edge, and that's good because then I'd have to subtract 1 from 2 coordinates and add 1 from 2. So the edges are how you can tell if something is a matroid. It's the Steinitz basis exchange axiom in a more polyhedral geometric form. These things are basis exchanges, and if all the directions in the convex hull are exchanges, you have a matroid. So this polyhedral point of view then lets you consider Well, subdivisions of matroid polytopes into other matroid polytopes, and these are the things Speyer took to define tropical linear spaces. Probably better if I go over there first, isn't it? Okay. Matroid subdivision is a way of cutting up a matroid polytope into other matroid polytopes. So you can say it's a cell complex whose cells and whose total space are all matroid polytopes. And from each such thing, we can construct a tropical linear space. I will mostly work on the matroid polytope side, but we can subdivide this. We can subdivide this guy. We just want to cut this into smaller polytopes in a way that doesn't create any new edge directions or any new vertices, any vertices that weren't at 0, 1 positions. So the kind of cut I could make, for instance, is I could cut this octahedron in half along one of the squares. I get 2 square-based pyramids, one right side up, one upside down. I'll just draw the maximal cells like this. And so their faces are the faces, the cells of the complex. The total space is this guy. And so 2 maximal cells. Here they are. And since I didn't introduce any new edges, I didn't ruin the matroid property. This is a matroid subdivision. And now from such a thing, you produce a tropical linear space. Well, at least if it's regular. Any regular matroid subdivision. So it's given by a height function, lifting things into one more dimension and then looking at it from below, say. Any regular matroid subdivision induces a tropical linear space. If I have a regular subdivision, I have a dual complex. I won't go into painful detail here because I'll be mostly using this perspective. But if I have a regular subdivision, I have a dual polyhedral complex structure in the dual space. Each point selects a face of the subdivision, and the points that select faces that are loop-free matroids where no coordinate is constant 0, those are the good points. Those are the points in my tropical linear space. Of all points in the dual space. Selecting a face not contained in the space where some coordinate is 0. So for example's sake, what does it look like here? Well, I've got my coordinates here. This face, for instance, on the side, 1, 2, 1, 3, 1, 4. No coordinate is constant 0 in this face, so this is a good face. So in my dual structure, I will have an array worth of stuff selecting this face. This front face, 1, 2, 1, 3, 2, 3, that's a bad face. X4 is always 0, so I won't have array selecting that face. And so on. I pick out all the good faces from here. Here I get one going through this front face and through the back one. And I get this, this shape of thing, which is, everyone's favorite tropical line in R3. So that's how you make a tropical linear space. Right. These objects are our protagonists, the geometries without geometry that David was investigating in his thesis. And, well, he had the natural question, I suppose, right? How how much combinatorics can there be here? If, for instance, if I took the matroid unsubdivided, this is a valid subdivision, and then I took the tropical linear space, I would get rays in the same directions. And, you can see from this top picture, I've sort of pulled the center thing apart, introduced more finite faces here. The finite, sorry, not finite, bounded. The bounded faces here correspond to the interior cells of the matroid subdivision. And it's, a natural extremal combinatorics question. How many cells, how many internal cells, interior cells, can you fit into this? How finely can you cut this up? Since there are only finitely many matroid polytopes, there is some maximum. What is it? And computational experiments, like you can generate random representable guys over a valued field. That's one way to construct tropicalizations. You can take tropicalizations of linear spaces, try things, and this is what David did. You'll find that there's a maximal combinatorics, which is kind of achieved very naturally in random examples. Sometimes it's less, but the upper bound, any upper bound kind of suggests itself to you if you sit down and look at enough examples. I'll state it in these matroid subdivision terms. These are dual pictures, so you can make the same statement on either side. Any matroid subdivision of, okay, there's an n as a parameter in my definition of matroid, so n is that n of, okay, another parameter is rank. The rank is the sum of the coordinates of any point in the matroid polytope. That has to be constant because these things have coordinate sum 0. It's the rank of the matroid in the usual sense, if you know what that is, of rank R. Has at most a trinomial coefficient, which I'll make sure I copy down correctly. R minus I 1 and n minus R minus I minus 1. Interior faces. If you want to count all the faces, it's not too hard to derive the count of all the faces from the count of interior faces. And this is the one where the number is nicer. But counting all the faces, you get a very similar sort of statement. And as I said, it's not too hard to stumble on examples where you achieve this. For instance, here, n equals 4, r equals 2. If I want I equals everything is codimension 1 or more in this picture. So if I take I equals 1, what do I get? 4 minus 1 minus 2 is 1. That doesn't seem right. Maybe this should be, okay, 4 minus 0 minus 2. Choose 4 factorial or 2 factorial, 2 factorial. That looks good. That gives me 2. And if I want faces of codimension 2, I get 1. So this is the kind of thing that attains the bound. And so Speyer conjectured this and was able to prove it with, definitely not without geometry, with complex algebraic tools. If all of the matroids involved, the faces of the subdivision and the total space are representable over the complex numbers, come from some linear space over the complex numbers. Complex represent. And that has stood open, and this is the thing that Andy and I have shown. In general. So that is what I want to talk about, how we do this. Hopefully not getting too nitty gritty, although there's some very nice, very powerful looking tools, right? Kind of in particular, these days, the matroid Hodge theory has been released and is knocking off all sorts of conjectures left and right. This is not the matroid Hodge theory. This is something else. And so hopefully I'll be able to say enough about it, to kind of make that difference appreciable. So the first, a lot of this was due to Speyer, in particular the approach to this. How might one bound something like this? Or consider the problem given a lattice polytope. If I want to subdivide it into lattice polytopes, can you give an upper bound on the number of top dimensional faces? Well, you can do that, for instance, by volume, right? Any lattice polytope has volume bounded below by that of the unimodular lattice simplex, 1 over n factorial. And the volume is additive, and so you can't fit more than that many things in there, no matter what you do. So that is one quick way to give an upper bound on the number of faces in, say, a lattice polytope subdivision. We'd like to use the same kind of idea here. We'd like to give some invariant of each piece of this subdivision, so that this bound will emerge by totting up the contributions of the pieces. So that is, this was already Speyer's approach. So we want to take something that is additive like volume, like a measure. Such things are called valuations in the polyhedral geometry world or in the convex bodies world. So I will specialize the definition to matroids and give it like this. So a function, let's say I want it to run from the set of all matroids. Maybe it can be the set of all matroids on n or something like that, into some abelian group. Is called a valuation. Leave enough space for a couple of letters here. I will amend the definition. Okay. If it is additive, I'll say this informally, additive in matroid subdivisions, in the inclusion-exclusion sense, or the measure theoretic sense. Yes. Oh, I'm people in the back can't see. Okay. Louder for the people at the back. Well, all right. Let's see how tall I can jump then. Okay. Thank you. All right. So, the kind of property one needs, for instance, in this example, right, is that if I want this function to be evaluation and I evaluate it on my octahedron, well, then my octahedron can be cut into the two square pyramids. But I have double counted the square. So I want to subtract off the square, and then I should have a relation like this. And this is perfectly fine, but just because there are pesky signs in here, right? There's a minus sign here, and if I want to think, well, I'm going to have some additive contribution, which I tot up from all the faces, it's just slightly nicer if we do it in a sign-free way. So you can take this definition and just alternate the signs in it. This is what tends to be called a co-valuation. And so instead of using inclusion-exclusion kind of, you can think, well, one way to get the geometry is like, think about the decomposition of the open polytopes. The open polytope is really the union of these three open polytopes, where this thing shows up as a contribution to the union. No overcounting and cancellation needed. Say of the like I'll just say with respect to open polytopes, interiors of polytopes. And then I really partition this interior into these three interiors. And so if I'm working with co-valuations, I turn that into a plus. And so all that co-valuations does is it removes the sign alternations in these identities you get here. And if we're trying to prove that things are positive, which is going to be the key question here, we want to prove that something is positive, strictly positive, bounded below in some way. Someone doesn't like co-valuations. And so when I add up all of these positive terms, I have a bound on how many there are. So that's for convenience. So kind of what we want then, I'll write what I said, strategy. Yeah. So define as I said, I'll use a co-valuation, which is this function g from the title, which, okay, now since I want it to be, I want to track faces of each dimension, so the tidy way to do that is to make some polynomial invariant where the degree of your variable records what dimension you're looking at. I'll index by codimension. Okay, so this thing will be valued in a univariate polynomial ring. And okay, really we want, okay, so that with non-negative coefficients, and if I have an I-dimensional face, a codimension I face, and well, let's say it this way, positive coefficient of t to the I, if M is a codimension I face. If you know the combinatorics, the codimension of this polytope is the number of connected components of the matroid. So a connected matroid, this codimension is 1. They're the full dimensional things here. And disconnected matroids give you smaller dimensional things like that square. And this way, right, each codimension I cell will contribute at least 1. And so then you evaluate your G on the thing you're decomposing. I guess on the hypersimplex, that's the biggest thing. You evaluate your G on the hypersimplex. And the coefficient of t to the I you see there is a bound on the number of positive contributions of t to the I you can have from the cell. So it's a bound on the number of cells of codimension I. Right, okay. So indeed, Speyer did this. Such a G exists. It is possible to say in combinatorial terms, or to characterize it in combinatorial terms, but the definition is kind of thoroughly algebrogeometric. So for the combinatorics fans in the audience, I'll give something that's not a definition first, but which is enough to work it out with if you're fluent with matroid combinatorics. Then I'll give the algebrogeometric definition. So kind of combinatorially, there is a unique co-valuation which is just some properties that fix it combinatorially, which is multiplicative on matroid direct sum, unchanged by series and parallel extension, and with G of a line segment, U12, is equal to T. Okay, and if you if you are adept with the matroid combinatorics, these properties will allow you to evaluate completely what is going on. So in this example, okay, any series parallel extension of U12, that thing is called a series parallel matroid. So any series parallel matroid is just going to get assigned T. Each of these square pyramids is a series parallel matroid. So this thing is going to get assigned T. This thing is going to get assigned T. There's a square in the middle. This is going to be disconnected. It's codimension 2. It has 2 components, but each of them is a segment, is a U12. So this is going to get T times T. And then it's a co-valuation, so it just adds. So the G up here is just going to be the sum of those things, 2T plus T squared. Corresponding to this maximal decomposition into 2 top-dimensional things and 1 common face. So, I mean, this is a little bit circular because I started from this decomposition, but because the pieces are series parallel, it's saying this is actually a maximal subdivision. Series parallel pieces are what are going to give you a subdivision that attains the bound. But okay, that wasn't a definition. So if we want a definition, we have to go to the algebraic geometry. Have to. Want to, finally get to go to the algebraic geometry. Okay, so how does one do this? So I want to start with, I guess I will write out a diagram. So I want to start with the with R and N having the meaning they do here. So I want to pick, I want to look at the dimension of R, Grassmannian of R-dimensional subspaces in C to the N. I'll work over C for now. If I have this Grassmannian, then right, this is meant to be the moduli of linear subspaces. So if I have a linear subspace L, or L, an R-dimensional linear subspace, then I get a point in the Grassmannian by the modular interpretation of the Grassmannian, by its reason for existing. And so if I have such a point, that point is going to give me a matroid, and I'll tell you how to cook up the matroid invariant for that matroid. Using the Grassmannian. Okay. So the other nice thing the Grassmannian has is a torus action. I will take the n-dimensional torus, split torus. This acts on the C to the n by scalar, by diagonal matrices. And so if I have a subspace, it acts on the subspace, and that induces an action up here. Okay? So then, well, in here, I can look at, take the point representing my space L, and just take its torus orbit. Take all coordinate scalings of L. Those have the same matroid anyway, same hyperplane arrangement even. So I get this torus orbit that goes in there, and I can take its closure, and closures of torus orbits are toric varieties for those who have seen them. So I get a nice toric variety defined through my point L, which in fact is going to be, well, if you know how to construct a toric variety from a polytope, it's just the toric variety of the matroid polytope I started with for this matroid. Okay. Now, what I want to do, I want to look at 2 line bundles on here. Again, the kind of natural line bundles that come from the Grassmannian's meaning as a moduli space. Each point of this represents a subspace of C to the n, so I can take the tautological line bundle whose fiber at L is L. I'll call this S for subbundle. So S is the line bundle. S is the line bundle whose fiber at any point L is just going to be L. Right? That gives me a nice rank R line bundle over the Grassmannian. Vector bundle, vector bundle. Thank you. And complementarily, a quotient vector bundle, where I look not at L, but I look at the ambient C to the n mod. So I have these two vector bundles that live over the Grassmannian, ranks R and n minus R respectively. Neither of those is usually 1. And now I would like to, well, in this case, I can just pull them back to here. I get two vector bundles on this toric variety. And I'm giving a slightly ahistorical telling here. Because, when David introduced this, he was working with this toric variety. And I wrote a paper with him not long after this in 2010. We were working with this toric variety. And now we have this modern language, sort of that came out of the integrating the stuff we did with the matroid Hodge theory program, which was this work of Birgit, Ur, Fink, and Tseng. Who were asking, well, this is all well and good if I have a matroid of a linear space, a representable matroid, but what if I don't? Well, yes.
You fix a point from the Grassmannian and then you define f based on that, right?
That's right. I fix a point. You can call this f of L. That's right. Yes. Okay. So if I have L, then I have f of L, and I have these pullbacks. What if I don't have L? So I don't have f of L. I'd still like to get these vector bundles because I'd like to define G using these vector bundles. That's what I'm building up to. And okay, so what these people, these four authors give a way to do this. And for various reasons, one of them being the importance of the permutahedral toric variety in the matroid Hodge theory, they pull back a little bit more onto the permutahedral toric variety. That's what this guy is going to be. So now I have, okay, let's call this composite G of L. Okay, not the same G as in my title. Let's call it H of L. Let's call this composite H of L. So then, in the same way, I can pull back via H, and I'm going to give those names. I'm going to call it S sub L will be my name for pullback via L of S, and Q sub L will be my name for pullback via L of Q. So now the base isn't a function of L anymore. Just these two vector bundles are functions of L. This is the setting in which these people work. We're going to do fairly birationally equivalent things. So this is a toric blowup. It won't so much matter if we work on this side or this side. David originally worked on this side. We've reinterpreted things on this side, but that's not really such a big deal. Okay. So what these people did is sort of wanted to produce analogs of these for non-realizable matroids that are not of the form matroid of some linear space. And okay, you can make vector bundles, in fact. You can make vector bundles in some sort of, well, I'll say this differently. The computations we want to do are things like taking classes of these vector bundles, Chern classes and things like that, Euler characteristics, operations that you can do within the algebraic K theory, whatever that is. We don't so much need to know what the algebraic K theory is here, but it lets us at the operations on vector bundles that we want. So that gives us some freedom. Maybe we don't construct literal vector bundles. Maybe we just construct classes in K theory that, are the classes of these vector bundles when they exist and are something else when they don't exist. And so these are classes. I guess I'll put them in square brackets because that is the usual notation for classes, S of M and Q of M in the algebraic K-theory ring, torus equivariant, of my permutahedral toric variety. And these are going to be my avatars of these, such that the class of S of L is the class of S of M of L, right? So if there is an M of L, then the class that I assign to the matroid should agree with the class that I get from the linear space. And if not, you present this ring in a combinatorial way, equivariant localization, and so that lets you describe elements in here using only combinatorial data, and a matroid is the perfect kind of combinatorial data that lets you do that. And I guess what the matroid Hodge theory says here is that these things, behave as if they belong to good positive Neff vector bundles. They have the kind of Hodgey positivity. That's not the positivity we're using, but they have the kind of Hodgey positivity that you can also wring out of these from like Adipresido-Hughat's theory. So that is one piece of evidence that these are really good objects, that are nice, that deserve investigation, even if they are geometry without geometry in this sense. Right, okay. So the definition of G then is given by doing some operation which, with the vector bundles in the case that they exist, and these surrogates in the case that they don't. Yeah, there's a fair amount of ghostwriting left over. Is that clean enough? Yeah, all right, good. Okay, so with this, we can finally define the object in the title. So now definition, right? This is kind of Speyer's definition reinterpreted by us using this Birgit-Urs-Fink-Tseng, because you can do the same thing on the toric variety of the matroid polytope. But we're just going to do it in the setting where we have these nice paper setting up these nice analogs. And just to get the indexing, the signs right, moving to co-valuations here means that the signs show up on the algebraic geometry side instead. Oh, well, you win some, you lose some. Okay. So what this says is that omega of M is, okay, -1. You have a sign. The alternating sign goes there now. And now you have a 0 to the rank of an Euler characteristic of, well, I'll write the thing as a class, right? The ith wedge power of the S tensor with the ith wedge power of the Q. So if these are really vector bundles, you can construct that tensor product of wedge powers, evaluate its Euler characteristic, and that gives you some number. If they're not vector bundles, but they're these things, you have like Adams operators on the K ring that let you interpret what this symbol wedge I of a class means. You have a product in the K ring which lets you interpret what tensor product of classes mean, and then you have an Euler characteristic now. And so this is still a perfectly cogent number. Okay, so there we go. That is the definition, and you check that this thing matches the combinatorial rule I gave before. So I will not, of course, be able to outline the proof in whole, but I want to kind of say what the kind of key techniques of the proof. So top level view of proof. Is that what I want to do now? Let me just make sure there's nothing I want to do first. Oh yeah, there's one reduction I have to make first, which is hot off the press. So Chris Shaw and David and I, 2 days ago on the archive, finally finished a paper which we started writing in 2016, which says if the top coefficient, the Rth coefficient, this is like a Bergman-Fad intersection theory computation. If the C to the R coefficient is non-negative, then so are the others, and then the whole conjecture is true. So since this is on the archive now, I don't have to talk about that. You can read that. I think it's 2411.19521. So I don't have to talk about that. I can instead focus on this coefficient and tell you how you handle that. Okay. So, well, let's just rewrite one thing I can do. Okay, what's this thing I'm looking at? Now I want wedge I. Okay, if it's the top coefficient R, wedge R of this thing, wedge R of this thing. Oh, and I missed a dual. Sorry, there's a dual on that one. Now, one nice thing here is because I have this exact sequence involving S and Q, because of the exact sequence involving L and Cn and the quotient by L, I can reinterpret this Rth wedge power as the n minus Rth wedge power of the orthogonal complement, which is this guy. So I can turn them both into Q duals, and that will be helpfully suggestive for what I'm going to write next. Okay. Good. All right. So, take a breath, take a drink of water, and let's write out the kind of key technique. Oh, there should be duals everywhere. I missed one, and then I missed two more. Right. Okay. Audience participation. Good. Okay.
So omega is the same thing as G?
So omega, oh my, sorry. This is G. That was, omega was meant to go here. Omega was meant to be our name for the top coefficient. Thank you. That, yes. G is the polynomial we were talking about. We look at the top coefficient, we give the name omega. Omega is the last letter of the Greek alphabet, it's at the end. Something I didn't say, the constant coefficient, which you might want to call alpha, is 0. The linear coefficient, which you might want to call beta, is beta. It's Krapos beta. Okay, so that motivates these Greek letters, so that's what we call the last coefficient omega. Okay. So, tools for the proof. Right. As a lot of these things go, if I have a matroid of a linear space, then I have a geometric picture. I can try to exploit the geometry. And then if I have some other matroid, I have to figure out something to do. And so, the way the tools for the proof are going to break down, well, there's the representable case. M equals M of L. And I really am working over C. We're using tools here which are really over C. And then there's the general case. And the package of tools we use in the representable case, well, two processes, really. Few words. One is probably unfamiliar and one is potentially familiar. Initial degeneration is something that many of us who work with computer algebra, we are fine with taking initial ideas. Okay, so people may have heard of initial degeneration. This thing, I didn't know about this work of Kempf 1975 until Andy did a deep dive, but what's going on here is if I have a vector bundle, okay, I'll just draw the whole thing here. Let's say I have a vector bundle over some base, and it embeds into a trivial bundle. Okay, trivial bundle, let's view it geometrically, trivial bundle like this. Well then, okay, so this map here, right, this geometric structure morphism, that is just, I look at E as a subset of this product and I project it onto the X. Okay, well, I have another factor. I can also project the thing onto the Cn, right? So this, I view this as like the second projection of E as it sits inside here. That's the structure map, is the second projection onto the second coordinate. And I can also project E onto the first coordinate. And if I do that, if I look at the image of that, the first projection, project away from the base, look at the union of all of the fibers of E over all points of the base. This is the thing that is called the Kempf collapsing. So this is projecting a vector bundle away from the base. Those are kind of the two steps. We want to start with our vector. We want to start with a suitable vector bundle on, well, it doesn't matter so much, xn on here. Project it into some just complex vector space, get some variety. Do an initial degeneration of that. Once you do an initial degeneration, you have a variety defined by a monomial ideal. You have a hope of applying combinatorics, right? So once you're here, you have some, okay, so this is some monomial variety. In fact, it's going to be square free. Some nice reduced union of coordinate subspaces. And so, you know, that's just combinatorics. Right now, we can hope to at least define what we should get if I started with an arbitrary matroid. So we can at least define it for an arbitrary matroid. But okay, these are the tools. How does the proof go? Well, the proof is basically sort of by tracking track free resolutions. We start with a free resolution of, well, we start with a Koszul complex, something which has lots of wedge powers in it. We start with a Koszul complex. We do this to it. There is a nice suite of tools for Kempf collapsing, especially this paper of Weyman from 2003, book of Weyman by 2003, Weyman's geometric method for syzygies, that says that this Kempf collapsing actually interprets a whole, or inherits a whole lot of properties of the vector bundle. So we can get a free resolution for the collapsed thing. We do an initial degeneration. Usually that makes free resolutions, at least minimal free resolutions, worse. But here we're in a magical setting where the minimal free resolution doesn't get any worse when you do this. We still have the same shape of minimal free resolution. And then we pick out the wedge powers we need out of that minimal free resolution once we interpret it via links of the Stanley-Reisner complex via Hochster's formula. Okay. So that's what we do in the representable case. And then in the general case, well, most of that doesn't exist. This exists, this class exists. The square free monomial variety, this simplicial complex exists. Nothing in between does. And so in the general case, what we show is that both the left-hand side, which is the definition of this omega of m, and the right-hand side, like the free resolution of the degeneration, are matroid valuations, right? Are this kind of linear function that we had before. And a fact is that up to these linear relations imposed by matroid valuations, the representable matroids span all matroids. And so you have two functions that agree on a spanning set of matroids, and so they have to agree. Yes. Yes, so I'm eliding here that you have, you have a square free monomial ideal, you construct a minimal free resolution for it, you can get the Tor groups out of the links, you have that thing. Representable matroids span all matroids up to valuations. Okay, and since there were a few minutes of announcement about cake and toilets, I will indulge myself in saying one more thing, one more surprise.
Valuations or co-valuations?
Well, it is, in fact, it's valuations here because sort of by looking just at this one coefficient, we have stripped out the need to alternate any signs. So I can say valuations. But the surprise is that it's actually bilinear functions. So it's actually bi-valuations because I can turn this, I had a pair of matroids in the title. I can actually do everything for a pair of matroids instead of just one. And there's no reason to do this if you're studying just Speyer's G, but it was kind of one of these cases where once you see the subject in its natural generality, you get many more hints what to do. So actually, we can do everything. Everything works for two matroids. The bundle we start with, right? I said we do some bundle, collapse it, degenerate it. The bundle we start with, the vector bundle, is the direct sum of two of these subbundles. Where these are possibly unrelated linear subspaces, no flag condition or anything, right? Just two linear subspaces of C to the n. If they're the same, then this gives you Speyer's G. Because you have things like this, right? Where I have the same m in both factors, right? So taking the same L in both factors will tell you about things like this. But if one of them is one-dimensional, then what you get is the work of Ardilla and Booker about the matroid Schubert variety, or about what's now called the matroid Schubert variety. So they went through, this whole process, starting with thinking of one matroid, and they didn't think of this as a parameter. It was just like the line spanned by 1, 1, 1, 1, 1. And they did this, right? They say you get this collapsing is what they thought of as the closure of your linear space in a product of P1s. That's what it turns out this is. You do the initial degeneration, and you get something encoded by the external activity complex of your matroid, and they describe the free resolution and so on. And it turns out that was the key to what we do. We generalize their external activity complex to the diagonal Dilworth truncation of the two input matroids. I'll write that sentence, but I'm over time, so you'll have to ask a question if you actually want to hear anything about this. And then I'll stop. All right. Love to end a talk with an undefined piece of terminology, but there we go. Thank you. Yes. Yes, okay. So so there is sort of these valuative relations that I gave like this. I mean, you could just look at the the group generated by all matroids and then mod out by the corresponding relations, right? So I could say this matroid, the class of this matroid equals this, right? So I could, if I take these relations and impose them on the matroids themselves, then I get some group generated by matroids with some relations. And okay, this group as a Z module, the representable matroids span it. No. You can see my paper with Dirksen for that. It's like Schubert matroids, in fact, span it. So you do like some Brion-Schongram game with any matroid, and you get Schubert matroids. So that's how you expand a matroid into Schubert matroids, and Schubert matroids are representable.
So this is not saying that every matroid can be subdivided into.
Right. It's not saying subdivide. Some matroids can't be subdivided at all, and so you can be stuck. But you don't only have to build down, you can build up, right? Any matroid, I can take a matroid and add more things. So every matroid can be put in a subdivision of the uniform, for instance. And typically the rest of the pieces are less unrepresentable than the thing you started with. So you can also sort of see it that way. Take your matroid, put it inside the uniform. The other pieces you get are milder. Maybe they're representable. If not, they're at least closer.